Welcome to the new era of video creation with Biozy 8. Today, we will explain the concept of catastrophic forgetting in neural networks. Explain the concept of catastrophic forgetting in neural networks, and how would you address this challenge when developing AI systems for continual learning. Catastrophic forgetting refers to the phenomenon where a neural network or AI model forgets previously learned information upon being trained on new tasks or datasets. This is especially prominent in continual learning or incremental learning scenarios, where a model is expected to learn continuously over time. The core issue arises when weight updates for new tasks interfere with the weights learned from previous tasks, leading to the loss of old knowledge. This can severely limit the ability of a model to handle multiple tasks in sequence without degradation in performance on older tasks. This is a major hurdle for building AI systems that need to adapt to new environments and continuously evolve over time without forgetting essential past learning. Continual learning is crucial in a wide variety of real-world applications. For example, robotics and autonomous systems must constantly adapt to new environments, obstacles, and tasks. A personal assistant AI might need to learn new preferences or tasks from users over time. However, one of the key challenges is to manage the balance between old knowledge and new knowledge. Without proper techniques to mitigate catastrophic forgetting, models may lose the ability to perform tasks they had previously learned. Additionally, systems with limited memory storage, like edge devices, may find it difficult to store all previous data, making continual learning more difficult. A good continual learning system must adapt quickly to new information without losing the performance it had achieved on earlier tasks. The core mechanism behind catastrophic forgetting is the weight interference caused by training a neural network on a new task. As the network is updated to learn a new task, the weights associated with the previous task may be overwritten, causing the model to forget prior knowledge. This is a key element of the plasticity-stability dilemma, which is the challenge of balancing the plasticity, ability to adapt and learn new things, and stability, ability to retain previously learned information, of the neural network. Additionally, training instability, such as vanishing or exploding gradients, can exacerbate forgetting by causing large erratic updates that interfere with the retention of old knowledge. Lastly, memory saturation can occur when the neural network has limited capacity, causing it to overwrite important information during training. Several strategies can be employed to mitigate catastrophic forgetting. Regularization techniques. These methods add constraints or penalties to the training process, which prevents the model from making drastic changes to weights already learned from previous tasks. The aim is to ensure that the neural network doesn't forget older tasks while learning new ones. Regularization can include methods like L2 regularization or dropout to control weight updates. Rehearsal methods. These methods involve storing a small subset of examples from old tasks and periodically replaying them during training on new tasks. This helps the model retain information from past tasks while learning new ones. One example is experience replay, where past experiences are sampled and used in combination with new data. Progressive networks. With progressive networks, new tasks are learned by adding additional modules to the network, allowing the model to learn new information without disrupting the knowledge already encoded in the existing modules. This technique allows a network to grow as new tasks are introduced. Elastic weight consolidation, EWC. EWC regularizes the update of important weights by introducing a penalty proportional to the change in those weights. This prevents the model from drastically altering important weights for previously learned tasks while adapting to new tasks. Elastic weight consolidation, EWC, is an advanced technique designed to mitigate catastrophic forgetting by introducing a regularization term into the loss function. This term penalizes weight changes that are important for previous tasks, effectively discouraging the model from altering critical weights. The importance of each weight is calculated using the Fisher information matrix, which measures how crucial a particular weight is for the accuracy of the model in the context of previous tasks. By penalizing significant changes to important weights, EWC helps the model retain previously learned tasks while still allowing it to adapt to new tasks. This method works well in practice, especially for problems where the task distribution is somewhat stable. But it may face challenges in highly dynamic environments where tasks and data distributions change rapidly. Rehearsal-based methods are one of the most intuitive approaches to dealing with catastrophic forgetting. The idea is to store a subset of data from older tasks and periodically replay it alongside the new data during training. This helps the model retain previous knowledge while also adapting to new tasks. A popular method is experience replay, often used in reinforcement learning, where an agent reuses its past experiences to prevent forgetting. Another example is memory-augmented networks, which use an external memory matrix to store important past experiences and replay them when training on new data. While these methods are effective, they come with trade-offs. Storing old examples requires significant memory overhead, and replaying the data can increase computational complexity. However, the benefit is that these methods help ensure that previously learned knowledge is not lost as new data is processed. Progressive networks tackle the issue of catastrophic forgetting by adding new modules to the network each time a new task is introduced. This allows the network to learn new tasks without disturbing the knowledge encoded in the previous tasks. In this approach, the weights of previously learned tasks are frozen. They are no longer updated as new tasks are learned. This approach is scalable, as the model can handle many tasks over time by simply adding more modules for each task. However, it does come with downsides. As new tasks are learned, the overall size of the model increases, which could lead to higher computational costs and longer inference times. In more complex or dynamic environments, catastrophic forgetting becomes more pronounced because the task distributions can change frequently. For example, in a real-time AI system for fraud detection, the nature of fraudulent activity evolves, requiring the system to learn new patterns while retaining the ability to detect old patterns. This kind of task evolution makes it harder for a system to maintain performance across all tasks simultaneously. To solve this, it is often necessary to combine multiple techniques, such as elastic weight consolidation, EWC, rehearsal-based methods, and progressive networks. These combined approaches can help mitigate forgetting while ensuring that the model can still adapt to new data efficiently, even in highly dynamic and evolving environments. To conclude, catastrophic forgetting is a significant challenge in machine learning, especially for systems that require continual learning. Solutions like elastic weight consolidation, rehearsal-based methods, and progressive networks have proven to be effective in addressing this issue. These methods allow AI systems to retain knowledge while learning new information, which is especially important for applications in fields like robotics, autonomous systems, and personal assistance. The ability to learn continuously without forgetting old tasks will be a key requirement for future AI systems, enabling them to function effectively in dynamic and ever-changing environments.